Hi everyone. Today we are going to be looking at density, and our two learning targets for today are applying concepts of density and modeling situations, and we're going to apply surface area and volume to solve design problems. Let's start looking at our background story. Luis has learned that before they make any decisions about changing packaging materials, he needs to make sure he is within budget for the cost of the packaging materials and the cost of shipping the product. The new material under consideration for packaging food products costs 45 cents per square foot. The shipping cost is $1.90 per pound. The table below shows the density for 4 different food products packaged in bulk and shipped from Luis's company. So below you can see we have the materials column, which we have shelled almonds, apple seeds, coffee beans, and soybean hulls. And then we have their density, and that is measured in pounds per cubic foot. Luis is analyzing the cost of the following 2 packages designs to determine which package makes the most sense for use for coffee beans. We can see we have our cone, and then we can see we have our rectangular base pyramid. So we can see the cone has a 5-foot diameter, and we know the radius is half of that. We don't know what that measure is unless, we take half of the total diameter. And then we have a height, and then we have our slant height as 6 feet. Then for our pyramid, we can see that we have a height of 6 feet. We don't know what the slant height is, that's S, but we do know the bottom, the rectangle, is actually a square base. So it's a 5 by 5 foot square base. Now let's start looking at what the questions are asking us to do with this information. We're going to look at the cone first. So it says the diameter, we know what that is, and the slant height, perfect. It wants us to determine the surface area of that cone. And then we have to find the cost of the packaging material. Now, off to the side, I wrote down the surface area formula for a cone, which consists of the lateral surface area, so kind of the surface around the cone, plus the area of the base. Now, we can break this down even more. Lateral surface area is found by doing 1/2 times C times L, and remind ourselves, okay, what does C stand for? C stands for the circumference of our circle, which is 2 pi times r times L, which is our slant height. Now, our base, the area of our base, well, it's a circle, so the area of a circle is pi r squared. So really, this is kind of the formula we're working with. Now, kind of to help us out to make this a little bit simpler, right? I could, if I'm multiplying by 2 and multiplying by 1/2, those will cancel out. So I'm just left with pi RL plus pi r squared. Now, looking at this, we can figure out what r is. That's going to be 1/2 of 5. So that's going to be 2.5. So that's what we'll plug in for r. And then our slanted height, which is represented by L, that's going to be 6. So let's plug in what we have. We are going to have pi times 2.5 times 6 plus pi times 2.5 squared. So let's use our handy dandy calculator. We're going to have 2.5 times 6. That's going to be 15 pi, and then we do 2.5 times 2.5, or 2.5 squared, and that's going to be 6.25 pi. So when we add those two together, we end up getting 21.25 pi. And then if we wanted to really, really get exact, right? If we wanted to put that in our calculator, we would end up around 66.76 feet squared. Because remember, we're looking at the surface area, 2-dimensional. It's like wrapping a present, okay? Now, here's the thing. We have to figure out what that cost is going to be, right? So we have to figure out what the cost is. So we're going to take that 66.76 feet, and we're going to multiply that by 0.45. Remember, up in our previous problem, it shows us that it is 45 cents per square foot, and we're working with square feet, so that's what we have. So when we put that into a calculator, we end up getting, and remember, we're talking about money, so we only want 2 decimal places. We're going to get $30.04. let's keep going with these problems. We're next going to look at determining the volume of the cone. So now we have to refer back to what is going to be the volume formula. Okay, so here's what I'm going to do now. I'm going to use a new color, and we're now going to look at the volume of the cone. Now, we just looked at volume of the cone, right? We just recently looked off of that. That's going to be 1/3 times B times H. Now, remember, B is going to be our base area. Remember that. And we can honestly use some of the information we already have above, right? So that's kind of what we're looking at up here with this pi r squared, right? So we know we're going to have this value we're going to be plugging on in for B. So let's say I worked across, so I have 1/3 times 6.25 pi, and then I'm going to multiply it times the height. But oh boy, this is where a problem kind of comes in. We don't have the height. But you know what we do have? We have a right triangle, and we have 2 of the sides. So let's use our favorite theorem, Pythagorean theorem, to figure out what that missing piece is. So we have 2.5 squared, and we're going to add it to h squared, and that's going to give us our 6 squared. So when we go through and do the work, right, I'm going to help you on out, we end up getting h squared as 29.75, and then when we take the square root of that, obviously we're going to have the square root of 29.75, and I know that's probably going to be a decimal, but I'm just going to keep that number for now and put that into play right here, just so I have more of an exact number. I'm not doing too much rounding. Again, if you want to, that's fine. Your number might be a little bit off, but I'm going to go ahead. I'm going to type that in my calculator right now, and we're going to see what we get. All right, so let's round to 2 decimal places like we usually do. So we get around 35 it's 0.699, so let's do 0.70. And again, we're looking at feet cubed because it's the volume. So remember, we're just looking for the volume of the cone. It doesn't have anything with cost, because cost is now relating to covering the material on the outside. So we can go ahead and put our volume as 35.70 feet cubed. Now let's look at part C. It says, what is the relationship among volume, density, and mass? I'm going to help you out with this. We saw this a while back earlier in the year, and maybe you've seen this in your physics class or one of your science classes, but we have density is going to be equal to whatever our mass is divided by our volume. Some people like to abbreviate it as D equals M divided by V. Okay, so now for the next part, D, it says we want to find the mass of the cone that's filled with coffee beans. What we're essentially going to do is we're going to rewrite this density formula where we're solving for the mass. So think of, how would I get M, the mass, by itself? Well, I would end up multiplying my density times my volume. So that's the formula that we're going to be using here. So we're going to have to refer back up to the coffee beans up in the table up here, since they give us the density, right? D equals 22 up at the top. Now, we're looking at cone. Do we have the volume? Yeah, we have the volume from our previous problem. So what we're going to do is, to find that mass, we have to multiply our density of 22 times the volume of 35.70. So I'm putting that in my calculator right now, going to figure that out. And I am going to end up getting 785.4. Now, I usually round to 2 decimal places, but it's okay since we only have 1 decimal place here right now. Cool. Now, looking at this, our mass going up to the top. The density is measured in pounds per cubic foot. We've already worked with cubic feet, so now we're going to measure this in pounds. So now let's find the shipping cost of our cone, now that we know the weight of it. Okay, so to find that, it would be, our cost is going to be however much the weight is, which is 785.4 pounds. Pretty heavy. Now going back up to the top, we can now reference the shipping cost. It's $1.90 per pound. So now that's actually what we're going to be multiplying by, $1.90 per pound. So we're going to go ahead, put that in our calculator, figure out how much it's going to take to ship all of those coffee beans. It's going to be a lot. I end up getting $1,492.26. Wow, it's crazy. Now for part F, it says, what is the total cost for packaging and shipping the cone-shaped packaged filled with coffee beans? Well, that's where we're going to take our cost up here of $30.04. And we're going to add that to the cost that we just found for the weight. $1,492.26. When we put that in our calculator, we end up getting $1,522.30. Now, on the next page, we're going to continue on with this problem, but we're going to look at the pyramid. So what I'm going to do is I'm going to take the picture of the pyramid, I'm going to bring it over to the next page. And I'm also going to consider the information about how much it costs for surface area and how much it costs for weight. All right, I went and turned to the next page and I brought over my clip art picture of my pyramid because we're probably going to be referencing that. Now, here's the time for you to make a prediction about whether you think the total costs for packaging and shipping our cone, if it's going to be more or less than our pyramid. So you go ahead, you make a prediction. Now, it could just be based on looks. It could be based on anything else. I mean, anything. And we don't have to explain our reasoning because we're going to see that at the end. But just go ahead, take a wild guess. Do you think it's going to be the cone? Do you think it's going to be the pyramid? What do you think it's going to be? All right. You know what? I think the pyramid is going to be greater than the cone. We'll see what this prediction is, and then we'll figure out if it's true or not. Now for 3/8, we want to find the cost of the packaging material for the pyramid's design. Referencing back to our other problem, this means we need to find the surface area of our pyramid. Surface area of our pyramid, it follows similarly to our cone, right? Because we're going to look at that's highlighter. We're going to try again with a pen. We're going to have the surface area of the pyramid. Now I'm going to abbreviate that SA. That is going to be our lateral surface area plus our base B. Now we can write our lateral surface area as 1/2 times P times L. Now P is the perimeter, L is our slant height. Now our base here, since it's a rectangle, we're just going to be multiplying, one side times another side. So finding that won't be too difficult. So looking at our picture, okay, we got to figure out what's really going on. Instead of using L for their slant height, they use S. We can change it back to L either way. We don't have to use S, just because it's a little confusing with the 5s, but we don't know what L is. So we have to use this idea, ready, our favorite theorem, Pythagorean theorem. We have this right triangle in here, right? And we're trying to find that hypotenuse. Okay, we know the whole length across here is 5, so half of it is going to be 2.5. So really, we have 2.5 squared plus whatever our whole height is, which that's 6. So plus 6 squared equals L squared. It's a similar triangle to our last picture, except 6 is not the hypotenuse this time. We're looking for what that is. 6 is one of the legs. So let's say we do a little bit of math. Got it. Okay, we end up getting 42.25 equal to L squared. And then when I take the square root of that, we actually get kind of a nice decimal. We end up getting 6.5 as L. So we're going to go ahead and put that in our equation below. So we have 1/2 times Our perimeter, right? Remember, it's going to be 5 times 4 because we're looking at the bases. And then we're going to times that by 6.5. And then we're going to add that to the area of our base. Remember, that's going to be 5 times 5. Okay, so we go ahead, we put this in our calculator. We end up getting a really nice number of 90. And we're looking at feet, and since this is surface area, it's feet squared. So now, in order to find the cost, right, we have to have the cost as that 90 times, remember, 0.45. That's how much it costs per square foot to ship this, and we're looking at money. So we put this in our calculator. We should get $40.50. Now, the next question says, okay, go ahead and find the shipping cost of the pyramid. That actually takes quite a few steps to kind of bring together. We did it in the last problem. We did it over a couple of the steps. So reminding ourselves of the density and mass volume relationship, figuring out the mass, then figuring out that shipping cost. So just as a nice friendly reminder, what we came up with on the other page to figure out the mass was that it's density times volume. So that's from the other page, just as a nice reminder. And again, we're still going to look at coffee beans. We're going to look at the density for that. So we know the density for coffee beans is going to be 22 pounds per cubic foot. And then we have to end up finding, okay, what's going to be our volume. So let's look at finding, again with the highlighter, let's look at finding the volume of the pyramid. And we're going to reference that formula. Similar to the cone one, right? The volume formula is going to be 1/3 times B times H. Now, reminding us, the B stands for the area of the base, which this one is really nice since it's a square. We already know it's 5 times 5 is 25, right? We're taking that from up here. And then we're multiplying it times the height, which, ding, we already know. Up here is 6. Perfect. So we don't have to do too much work. It actually comes out being 50 feet cubed. So over here, our volume is 50. So now plugging this information in, we're going to get our mass as 22 times 50, and we're going to go ahead and put that in the calculator. Wow, we end up getting 1,100, and we want to label that as pounds. So that's how heavy, wow, that's how heavy it is to ship all the coffee beans. Ooh, hope people like their coffee. Okay, so now we got that part down. Let's go ahead and figure out what that cost is going to be. A couple colors in this problem. All right, so we have the 1,100 pounds, and we're multiplying it by how much it costs per pound. This was from the initial directions. It was $1.90 per pound. So when we end up doing that math, we get $2,090. So that's the shipping cost for the pyramid. So last but not least, we're going to add together the total cost of packaging and shipping. So that's taking this cost of $40.50 and adding it to that cost of $2,090. So when we add those two together, we end up getting $2,130.50. So now, here's what it wants us to do. So we can't get too ahead of ourselves on this. We got to look at the next question before we can really answer what's happening. We want to compare the ratio of the total cost to ship each package to the volume shipped. Remember, one is going to have more volume, but we don't know if that's, the best cost efficiency, right? Just because something's bigger doesn't mean it's the better way to ship it. It's like when you go to a store and let's say you have a cereal box. And then there's a bigger cereal box. And sometimes on the price tag, it tells you like what's the price per like ounce or what's the price per unit. And you want to try to find the smallest number possible. You want to find, okay, what's the bigger bang for my buck? Yes, I might be getting more, but I might be paying more with the cereal. So that's what number 4 is asking. So let's look down here at number 4. We're going to compare the ratio of the total cost to ship each package to the volume shipped. So we're going to do that with the cone. And we're going to do that with our pyramid. So that means we have to take whatever the total cost to ship it is and compare it to the volume. So I'll reference back to the other pages so that way you don't have to, flip back and turn your page in your textbook or your digital textbook per se. Okay, so for the cone, it cost $1,522.30. For our pyramid, we have that right above. It was $2,130.50. Now we have to divide those by the volumes that we found. So the volume of the cone, we found that out to be 35.7 feet cubed. And here for the pyramid, we got an even 50 feet cubed. So now we're going to put those in our calculators and we're going to figure out the money per feet cubed it costs. That's kind of what we're looking at. We're going to look at and see what we fill in. Oh boy, this is exciting. Let's see what happens. Okay, when I plug in the first value into my calculator, now I'm going to, let's say round 2 decimal places, we get $42.64. All right, I'm going to plug in the next one into my calculator. Let's see what we get. Oh my gosh, this is so close. $42.61. Oh my gosh. So looking at this, the cone costs more. It costs more for that total cost with the volume, that ratio. It costs more than the pyramid. Wow. Oh my gosh, this is so interesting. Like, if you look back at my prediction above, I was incorrect. I was going off of a blind guess like you. Who knew? Right? So it's really the other way. I should probably change that. That's so interesting. Cool. Did you get the prediction right? So now, moving on to number 5. It wants us to look at which food product in the table would be the least expensive to ship. And we got to start to figure this out as well, referencing kind of what we talked about with the coffee beans. So think about this. We are probably looking at what is the lowest density. Overall, the mass for a given volume is less. So let's think about what I just said. So let's zoom out. Let's take a step back. So looking at this, if we have a low density, that means our mass is going to be less for a given volume. And that's kind of what we want to look for as we're approaching this. So looking back at the other problem, which out of those products has the lowest density? So look back at that table. We're seeing it's the soybean hulls, right? They have a density of 6 pounds per foot cubed. So that's what we're going to work with. We're going to say the soybean hulls, since their density is lowest. Remember, overall mass for a given volume is less. Here's what I'm going to have you do now. You're going to go ahead and try number 8 on your own. So let's just read through it so that way you can see what we're going to be looking at. So butter has a density of 54 pounds per cubic foot. It is packed into a 5-inch by 1.27-inch by 1.27-inch cardboard prism. So think about that. It's going to be rectangular. That's what we're going to look at, okay? So one package of butter contains 4 identical prisms. So what is the approximate mass of one package of butter? So you're going to try this problem. It's going to take a couple steps and really looking over this and thinking it through, but use the ideas that we've seen before. You can go ahead and after you take notes and submit your notes, then you can go ahead and check your answers on this problem.